Hi there, I'm Ali, and here with Mohsen we're going to present to you DecompX, an explanation method for transformers decisions by propagating token decomposition. This is a joint work with Mohsen, Ehsan, Yadullah, and Tahir. In an explanation method, we want to know how much each token contributes to the model's final decision to explain the model's behavior. As shown here, explanation methods could either show the amount of influence, or which in our case, the direction of influence of each input token in the model's decision making. And a common solution for explaining multi-layer encoder-based models is to explain each layer with an attribution score map. Each point in these maps is a scalar score that explains how much an output token is influenced by an input token in that layer. These maps could be derived from various methods. However, to have an overall explanation for the entire model, and since the map only explains the model on a single layer, an aggregation method is necessary. Previous studies used scalar aggregation solutions like rollout or flow to aggregate multi-layer attribution maps into a single global map. However, the assumption of scalar cross-token attributions could be naive, especially for multi-layer aggregations. For instance, the relation between these two tokens in the second layer may have a different effect on each type of the attributions in the previous layer, since each of the input tokens could have a non-uniform multidimensional impact on the layer's output. Therefore, we propose DecompX, where instead of computing a single layer scalar attribution map, we decompose representations into its constituent vectors. Each of these vectors represent a part of the file representation that is attributed to a single input token of the model. Since we're interested in the whole model's behavior, our method should consider all layers' inner workings. Therefore, the main challenge would be to propagate these decomposed vectors from one encoder layer to another. To better define the decomposition term, encoder layer L representation could be broken down into n vectors, where n is the number of input tokens. Each represents the contribution of input token k of the model's input to the ith token in layer L. In the following, we briefly explain the formulation that how we could determine the decompositions for the output representations by having these input decompositions. But for extra details on the following equations, please refer to our paper. First, we plug in the decomposed vectors from the previous layer to the multi-head attention. Then we have the first add a normalization in the attention block. But here would be a main hurdle for continuing the decompositions further. Since the feed-forward networks feature a nonlinear activation function, passing down the summations as before would not be possible. Therefore, we linearize the feed-forward networks based on the activation point they have in the normal inference, and then we continue with the propagation. Then, after passing through the output at a norm, we will reach to the decomposed vectors of the output representations, which in fact are the inputs of the next layer. Using this method, we could propagate the decompositions throughout the whole model. In the end, we could have the output representations of the model decomposed based on the model's inputs. For a sequence classification task, the classification head is over the first token of the model. As this head is a feed-forward network similar to the one inside the encoder layers, we apply the same propagation method to decompose the output logics based on the model inputs. Note that this approach could also be applied to any other task structures like MLM or question answering and so on. So in total, our main contributions could be rounded down to 3 points: incorporating the feed-forward network, decomposing the representations based on the input contributions by using vector propagation, also incorporating extra overhead modules such as the classification head.
Hi, I am Mohsen and I will continue the presentation from here. We evaluate our method's faithfulness by perturbing the input tokens. We mask k% of the most important tokens based on each explanation method and measure the change in the predicted class probability and accuracy. When there is a greater change It suggests a more faithful method because the tokens having higher scores were truly important that masking them caused the model to considerably change its decision. In this setup, DecompX outperforms other explanation methods, both vector and gradient based, by a large margin at every masking ratio. And this result isn't limited to one dataset. We tested our method on 4 datasets using 3 metrics and 2 models. In all settings, DecompX was significantly better than the other explanation methods. So, I am excited to share with you our online demo. In this demo, you can input a text and see how the model operates to make a decision. You'll be able to see the positive and negative impact of each token on model's decision-making process. We also have a collab demo where you can give any checkpoint of Bert or Roberta and see the explanations. So please make sure to check out our online demo at the link available on the screen. Thank you for your attention, and please feel free to contact us if you have any questions. Thanks.